substance that gives a definite color in an acid and a different definite color in bases. There are three types of indicators. 1. Acid-base indicators. 2. Commercial indicators. And 3. The universal indicators. So I am sure you've heard of indicators before. Maybe the indicators of a car, which show the direction to which the car is moving if it is about to take a corner, and so on and so forth. Now in chemistry, indicators mean different, slightly different. They give the color, a definite color in an acidic solution and another definite color in a basic solution. So they are actually meant to classify substances as either bases or acids. Let us now look at the preparation of simple acid-base indicators. How can we be able to prepare these acid-base indicators in the laboratory? Now, step number 1, crush colored leaves or flowers or roots in a mortar using a pestle. So when you decide to use leaves, you use leaves of the same plant and of the same color. If you decide to use flowers of the same plant and the same color, then roots also make sure they are of the same plant, of the same color. So then you decide, for example, we can decide to make indicators using sukuma wiki leaves. So you crush the leaves in a mortar and pestle, add propanol, continue crushing and filter to obtain a thick color paste. Then the resulting paste is a simple acid-base indicator which can be confirmed by adding a few drops of it in an acid solution and a basic solution. So you will realize that they give a certain color in an acid and some other color in a base. These acid-base indicators, which are man-made, have some disadvantages. And these are the disadvantages. 1, they give inconsistent results. You will find that, for example, in a solution of sodium hydroxide, which we know it's a base, they may give a green solution. In a solution of ammonia, which is also a base, they give another color, maybe black or green-black color. So that means the results are not consistent at all, and that is a disadvantage. Now, the other disadvantage is that they expire within a very short time. For example, when you prepare an extract from sukuma wiki leaves, it will be green at the beginning, but as time goes by, after like 30 minutes, it will have turned black. So it expires within a very short time. Let us now move on to commercial indicators. These are commercially prepared and they are the ones which are commonly used in the school laboratory. They are very consistent in results and they do not expire easily. So they are able to cover all the disadvantages which are found with the acid-base indicators. They give consistent results, they do not expire easily, and they are normally, they can stay even for years in the laboratory without getting spoiled. Now, color of commercial indicator on acid bases. Now, the commercial indicators we are talking about, we have phenolphthalein indicator, we have the litmus indicator, and methyl orange indicator. And their colors in different solutions. For example, phenolphthalein in an acid solution it's colorless, in a basic solution it's pink, and in a neutral solution it's colorless. Let us go to litmus indicator. It is red in an acid solution, it is blue in a basic solution, and it is purple in a neutral solution. And finally, methyl orange, which is pink in an acid, it is yellow in a base, and it is orange in a neutral solution. So those are some of the different colors that show when different indicators are used on different solutions. Now, the advantage of methyl orange indicator over phenolphthalein indicator is that it gives different distinct colors in acids and neutral solutions, while phenolphthalein does not. So look at the different colors in methyl orange. In an acid it is pink, in a base it is yellow, and in a neutral solution it's orange. While phenolphthalein is colorless in both acidic and neutral solution. That is a disadvantage of a methyl orange. Now, let us move on to the pH scale and the universal indicator. What is a pH scale? Now, a pH scale is a numeric scale ranging from 0 to 14 used to specify the acidity or basicity of an aqueous solution. So it is used to specify the acidity or basicity of an aqueous solution. Now, the universal indicator, on the other hand, is a mixture of many indicators. It shows a range of colors in acids and bases depending on their strength of the acid or the base. So, the universal indicator is normally a mixture of many indicators, and it shows a specific color depending on the strength of the acid and a base. When drops of universal indicator are added to a solution, the color obtained is compared with that of a pH chart to determine the pH of the solution. The pH scale is shown in the table below. Now, a universal indicator works together with a pH scale. When you put a few drops of the universal indicator in a solution, then it will show a certain color. That certain color, you look against a pH chart and it will tell you the pH of that solution. And we said pH is the degree of acidity or alkalinity of a substance. So apart from the universal indicators telling us whether a substance is an acid or a base, it also has the ability to tell us how strong and how weak that base is, depending on the pH of the solution. Now look at the diagram. It shows a pH scale. You can see it has different colors with different pH scales ranging from 0 to 14. Now it has that part between 0 and 6, which is acidic. At 7 we have the neutral solution. Then all the way from 8 to 14 we have alkalinity. Now we have strong acids ranging between 0 and 4. Then 5 and 6 is for weak acids. Then from 8 to 10, that comprises of weak bases. Then from 11 all the way to 14, those are strong bases. So that is what this particular chart is all about. Now, what are some of the advantages of the universal indicator over other indicators? Now, the advantage of the universal indicator over the other indicators is that it gives information whether a substance is a strong or a weak base or acid. Like I have explained above there. You see, the solution will show a certain color when you put the universal indicator in it. So you are able to tell whether whatever you are checking is a strong acid, a strong base. Is it a weak acid or a weak base, or is it neutral? So apart from stating that a substance is an acid or a base, it goes a step further into determining whether it's a strong acid or a strong base. How do we determine the pH of substances using the universal indicator. Now this is the procedure. If the substance is a solid, add distilled water and stir it to dissolve into a solution. Then dip the universal indicator paper or add a few drops of the universal indicator into the solution formed. And the resulting solution then match the color with the pH chart. So if a substance is a solid, you must first dissolve it in water. Then the universal indicator also occurs in two forms, in form of a paper and in form of a solution. So if it's a paper, you just cut a little piece and throw it inside the solution and check the color of the paper against a pH chart. If it is the solution, then you put a few drops into your sample. Then you check the color change. Then you check it against a pH scale and see what the pH reads. And that will tell you whether your solid is a weak acid or base or a strong acid or base. Now, if whatever you are testing is a liquid, then dip the universal indicator paper into the liquid or add a few drops of the universal indicator solution into the liquid. Then match the color with the pH chart. And you'll be able to tell whether your liquid is a strong, weak, base or acid, or strong, weak, base or acid. Let's note this. The pH values for acids range from 0 to just less than 7. Weak acids are acids that do not dissociate completely in aqueous solutions, and examples of weak acids are lemon juice, orange juice, ethanoic acid. Those ones have pH values which range from 4 to 6. Strong acids are acids that dissociate completely to give out many hydrogen ions in aqueous solutions. They include sulfuric 6 acid, hydrochloric acid, nitric 5 acid, and their pH ranges from 0 to about 3. Those are strong acids. Now, the pH value of bases range from 8 to 14. Weak bases are bases which do not dissociate completely to give many hydroxide ions. Examples of weak bases are soap solution, calcium hydroxide solution, and toothpaste. Their pH values range from 8 to 10. Strong bases are bases which dissociate completely to give many hydroxide ions. Examples are solution of sodium hydroxide, potassium hydroxide, which have pH values ranging from 11 to 14. As the pH values increases from 7 to 14, the strength of the base also increases. And that marks the end of bases, which was our lesson for today. Attached are some revision questions. Please look at them and attempt them and ensure you are able to answer them correctly. Otherwise, let's meet in our next lesson. Be blessed and bye.